New results on crystalline graphene multilayers, intervalley coherence, and emergent spin-orbit coupling.
Okay, thanks everybody. I'm sad to say this is the first time I've had to commute to give a talk at UCSB since my family is in LA for Passover. So this was a little back and forth. So hopefully I won't be too scattered after the drive in traffic. But I thought today I would share some a little bit of overview and then some new results on these systems that we've been working on the last couple of years, which are really pretty simple and about which we're still quite confused as far as mechanisms and interpretation of phenomenology. So to give some background, a few years, I think that the sort of overall summary in the first few slides is that a few years ago it seemed like the key to getting strong correlations into graphene systems was to turn on a superlattice potential. This was manifest in two systems that emerged around the same time, magic angle twisted bilayer graphene and rhombohedral trilayers aligned to HBN, which both showed signatures of magnetism, superconductivity, and so on and so forth. Okay, and I think the basic message of this talk, before I get to sort of the details of new results that are not published, is that it actually seems, from our current point of view, that really what's important is just high density of states, and the details of the lattice are not particularly important. This is basically follows from sort of a simple, textbook physics of metals. For magnets, you have the Stoner criterion, basically says, whatever your Coulomb repulsion is, if you can get your density of states high enough, you'll have some magnetic transition. BCS superconductivity, also, if you increase density of states enough, you decrease the energy cost of building in some superconducting correlations to your ground state. And indeed, this is just sort of what's played out in a pretty dramatic fashion in these systems. Okay, so the systems that I'll talk about are mostly in the rhombohedral class of graphene multilayers. So this includes sort of exotic metastable multilayers, ABC trilayer being the first one. So these are not actually thermodynamically stable, but they are thermodynamically metastable. So ABA Bernal stacking is the ground state of graphite structurally, but ABC is actually pretty stable. You can isolate these structures relatively easily just by exfoliation and finding them. But another one in this class is Bernal bilayer graphene, which is actually absolutely stable, and it's sort of the conventional graphene bilayer that people have studied for many years. And they all share the basic features that with zero applied electric field, they have usually 3 Dirac points. They're single particle band structures described by 3 Dirac points that touch. And if you zoom out a little bit, it's a parabolic band touching. It's only at very low energies that this happens. But when you apply an electric field, you basically gap out that parabolic band touching or cubic band touching or quartic band touching that you get for these higher levels of higher numbers of layers. And you get some Van Hove singularities either at or very nearly at or somewhat nearby the band edge. Okay, and the ones we're going to be most interested in this talk happen for hole doping, due to just the details of this band structure. There, the Van Hove singularities are much closer to a sort of finite density saddle point where you have pockets around each K point that start to touch at some finite momentum, and you get a divergent density of states. And over the last couple of years, it's just been a total zoo in terms of really reproducing and extending the type of physics seen in moiré structures to these structures that don't have a moiré lattice. So these are very clean samples. They're ballistic on many micron scales, as I'll show you, which is about as big as we can make the device. They're highly reproducible. And without doing much, you find spin and valley ferromagnetism. I'll show you today signatures of nematicity and intervalley coherence. And tons of superconductivity, spin singlet superconductors, spin triplet superconductors that come out of a fully spin polarized ground state. I'll show you today that when you add spin-orbit coupling, which you can do controllably in these systems, you can get icing superconductors, which are a mixture of triplet and singlet, and some new effects that I haven't heard of in any other systems, like new mechanisms for spin-orbit coupling that don't come from the usual atomic spin-orbit coupling. So that's basically the sort of outline of my talk. So let me sort of introduce you to these systems. So, part of the virtue of these systems from an experimental point of view is that you can really understand them very well because they're very clean and you can make them over and over again and they're the same. which is not something that's true of twisted bilayer and related structures. So to give you an example of one of the tools that's really useful in our toolbox, this is a map of magnetoresistance of rhombohedral trilayer graphene. And I want you to notice the Y scale. This is from 0 to 1 Tesla. And you have tons of quantum oscillations really in the very low field limit because these are very clean samples. And what we can do is we can use this to map out the Fermi surfaces in these structures and try to figure out, exactly how well do we understand the band structure, what's a correlation effect, what's not a correlation effect. So quantum oscillations probe the extremal Fermi surface area. You usually do this by taking Rxx of 1 over b and doing a Fourier transform. Because we vary the density in these systems, it's useful to normalize that frequency that you get, which tells you the area, by the Luttinger volume, so that you're actually measuring, I'll plot the fraction of the total Luttinger volume encircled by a given quantum oscillation. So this is what that data looks like when you do all of those things. So I'm going to plot it as a function of f nu, which is this fraction of the total Luttinger volume that a quantum oscillation is probing. And you can see that, so this is again ABC trilayer graphene at 0 electric field, and it's mostly single particle physics. So if we go out at high density, we see that there's a strong peak at f nu of 1/4. That's just telling you that you have 4 Fermi surfaces that are the same. Okay, which is exactly what you expect in graphene because you have spin degeneracy and Valley degeneracy. And so you expect 4 flavors, and you expect at the single particle level that at high density you just have 4 very simple, simply connected Fermi Cs. Nothing is particularly special. As you lower the density, you see that this quantum oscillation depins from 1/4, and it's joined by another one at very low density. And actually there's a sum rule which returns the Luttinger volume if you take this frequency and you subtract this frequency and multiply by 4. And that's what you expect as you go through this Lifshitz transition, which is again there in the single particle band structure. It's nothing too interesting. But you can see it really clearly that there's this broad range where you've gone through this Lifshitz transition. Now you have an electron-like as well as a hole-like Fermi surface. Okay? And then if you go to very low density, you see that all of this is gone, and now you just have a very strong peak at 1/12. And 1/12 is exactly what you expect at very low density once you're past that saddle point Van Hove singularity, right? And now you have 3 pockets per flavor, so 12 total flavors. And the Van Hove singularity apparently is right there. And nothing too interesting happens for holes, actually, at 0 electric field. But there's one interesting thing here, which is for electrons, right at the Van Hove singularity, you see that this quarter peak is gone. The 12th peak is not there yet, but there's a little region where you just get a peak at 1/2. And that's because you basically have formed a half metal. So the system is completely polarized into 2 out of the 4 flavors for this very, very narrow range of displacement, a very, very narrow range of densities right near the Van Hove singularity. Okay? Now, what's amazing is that this is sort of the 0th order thing. This is where you don't have very strong Van Hove singularities. Now you can crank up the electric field, and what you see is actually that half metal state here is that light, tiny little feature. But as you increase the electric field, it's joined by all of these different very strong features. What I'm plotting here is actually electronic compressibility, or rather inverse compressibility. So where you see these bright blue features, that's where the compressibility is negative. And each one of these is basically, these strong ones are first order phase transitions between different types of ferromagnetic states that polarize into one or more of these spin and Valley flavors, and additional broken symmetries as well. Okay? So just to give you an example, right, if I take this Fourier transform out here at high density, even at high electric field, I find that I have my peak at 1/4, and that's precisely my symmetric state. If I then cross this first order phase transition and measure quantum oscillations in this phase here, I get a peak at 1/2. That's what I showed you before. This whole phase has 2-fold degeneracy rather than 4-fold. And if I keep lowering the density, I get a peak only at 1. So I go from a symmetric metal, spin and Valley symmetric metal, to what turns out to be a spin polarized half metal. So it's all one spin flavor, and both valleys are equally occupied. And then finally, a spin and Valley polarized quarter metal. Okay? And you can tell, that this is spin polarized and this one is also Valley polarized from things like anomalous Hall or in-plane field dependence of these phase transitions. That's all something that you can work out pretty directly, especially for electrons here, which are quite simple. But, so this was already kind of, just to give a little bit the history, which was kind of amusing. We stared at this for a long time thinking, God, how is it possible that we don't understand the single particle physics of ABC? Because of course, without a Moiré pattern, there's no interactions are not going to be important. That was wrong, right? So eventually we figured out this is all Stoner physics. Then we thought, okay, great. Well, of course it doesn't superconduct, so, we'll just understand exactly the details of all this ferromagnetism and we'll understand, why the Moiré systems superconduct and these non-Moiré systems don't. And in the process of that, of course, we found that they do superconduct. They superconduct all over the place, right? It's not the last time in this talk that I'll tell you about being surprised because we thought we were being careful scientists doing a control experiment that was going to crack everything open, and then you find that your control experiment is more interesting than the experiment you were trying to do. So indeed, this is, this same phase diagram, right? I showed you in compressibility all of these different phases, but it turns out that at the boundaries of many of these phases, there are superconducting states. So I call them superconductor 1, 2, and 3 here. I'll get back to these later. TC is relatively low for ABC, right? The highest TC is superconductor 1, which is sort of the best form. It's about 100 millikelvin. Okay, superconductor 2 is more like 30 millikelvin, as is superconductor 3. They're both sort of relatively low TCs. Now, I'm going to tell you about some of these superconductors and give you kind of a summary. I'm not going to try to tell you about all of them because at this point it's like 3 or 4 or 5 papers and it's more than I can fit in this talk. But one of the things I want to point out, so I'm showing you here scanning probe magnetometry data using nanosquid on tip microscopy, comparing that same ABC sample with ferromagnetic twisted bilayer graphene sample in the quantum anomalous Hall state. And I want to point out that this is a micron scale bar here. And you can see that basically the magnetism is essentially uniform over this whole flake. There's a couple of small bubbles. These are actually residue at interfaces that are introduced during the fabrication process that have to do with the fact that at this particular spot, because there's residue underneath one of the gates, you're not at the same density and displacement field as you are elsewhere. But basically, it's uniform. This is just the shape of the device. Whereas twisted bilayer graphene, actually the scale bar here is about double, but it's extremely non-uniform. And we know that this comes from twist angle disorder and the fact that, twisted bilayer graphene is not a structural ground state. It's not even a metastable state. It's just unstable. So you're trying to quench whatever strain happens to be there during your fabrication process in a particular way. Okay, so there's no analog of twist angle disorder here because there's no Moiré to be disordered and there's no twist angle to worry about. Okay, and that's really quite useful, as I'll show you. So, hold on, so before I go on to sort of the details of superconductivity and so on, I just want to point out that with no disorder, you really have a lot of possibilities. That's kind of the theme of this talk, right? So some years ago, you can certainly put a superlattice back without introducing much disorder. So in particular, by adding hexagonal boron nitride that's aligned, you can bring back superlattice potential, which can give you things like insulators at finite density. That's a lot of the work from Berkeley on ABC, on HBN. At high magnetic fields, we use this to show that there are fractional Chern insulators and partially filled Hofstadter bands a little while ago. Also, once you don't have intrinsic disorder in your 2-deg, we have a lot of technology in this field, especially from the study of fractional quantum Hall, to do really careful mesoscopics experiments, right? And so, for example, we have ways of doing local gating where we can really make locally defined potentials on the sort of 10 or 100 nanometer scale without introducing additional disorder to these systems. So I'll just advertise this paper that I won't talk about where you can actually realize, universal Cairo-Luttinger liquid tunneling between a 1/3 state and a nu equals 1 fractional quantum Hall state. This is all technology that's just directly applicable to these types of superconducting and ferromagnetic states. So just to inspire a little bit of thinking about, superconducting mesoscopics and, that combination. I know Charlie saw that a little bit recently. I think there's a lot of opportunities here which are really going to be, different than what's been done before. But, going on, to think about superconductivity, what can we figure out? What are these superconductors? One simple thing you could try to do is estimate whether they're dirty enough that they should be S-wave. Turns out that's not very useful here because you can measure the coherence length and it's a couple hundred nanometers, which is actually pretty long by the standards of, let's say, twisted bilayer graphene. But the mean free path is many, many microns. You can see that because you actually see ballistic electron focusing over, the size of the device basically between contacts as you apply some magnetic field. So this is, it's great because the systems are clean. It's not great because it doesn't solve the superconductivity problem. So, okay, so how do we figure out what's going on with the superconductor, right? We're going to first start by using quantum oscillations just to understand what the normal state is. Okay, so here's superconductor 1 in ABC, and I'm showing you the quantum oscillations above plotted as a function of B. Now that's not very useful, so it's nicer to plot them as a function of this F nu so we can understand what are the Fermi surfaces. Okay, and what we find is that the normal state of superconductor 1 happens from Fermi surfaces that are simply the single particle Fermi surfaces. There are no symmetry breaking yet. Okay, so you see that you're basically decreasing the density. This is exactly that Lifshitz situation where you have annular Fermi C, and you have a hole-like Fermi surface on the outside, and then you have an electron-like pocket inside. It's all consistent with single particle physics. And then you go into this superconducting state, and then there's a sudden transition to some other state that's broken some symmetry. You see that this is something close to a half metal, but actually it's partially isospin polarized. You have big and small Fermi surfaces that sum up to 1/2. But there seems to be a relatively sudden transition. Now, something we found out only quite recently by doing really careful thermodynamic measurements, that phase transition is actually first order. So what I'm showing you here is just a more careful measurement than we were able to do in the original paper. It wasn't clear originally whether this transition from the state that's superconducting into this other isospin polarized state is first order, but you can see this negative compressibility spike. That negative compressibility spike happens when you have a first order transition. You have two phases, they're crossing, and so the curvature of the free energy is just going to have some, it's going to be opposite sign when you cross, and that's sort of how that shows up. And this is very well known from, similar experiments, let's say on fractional quantum Hall systems and so on. So it looks like you have a spike, a negative d mu dn. It corresponds to a change in chemical potential of about 1 Kelvin. I mean, of course, I can't guarantee that there's, the susceptibility to this or that order is not very large on this side of the transition, but every experimental thing that we can say, it looks like the Fermi surface out of which this superconductor emerges just has no broken symmetries, and the phase transition is at least weakly first order, and it sort of looks, much more like a competing scenario where, you're turning up density of states. As you decrease the density, you're approaching this Van Hove singularity, you get superconductivity first, and then you stoner, and then of course everything is different and you don't get superconductivity again. Now, it so happens that you stoner into some phase that breaks some symmetries, then you do another transition into a totally spin polarized phase, and then you get superconductivity again in this system from a totally spin polarized phase, and then the same thing happens again. So superconductivity clearly, here it emerges from a state that, as far as we can tell, doesn't have any broken symmetries. It also can emerge from phases that do have broken symmetries. But as I'll show you, superconductivity is just totally generic in these systems. To me, that sort of points to some generic mechanism, which I'll leave to your imagination. So okay, it turns out that this physics is not specific to ABC. The story here is that, we were thinking through why ABC, why is it special? It superconducts, it's ferromagnetic. But of course, Bernal bilayer can't be special. But why not? Because it has essentially the same band structure. Almost all the physics should be the same. And we, of course, had these on the shelf, because this is the same sample that we used to study, fractional quantum Hall for many years. But if you look carefully at Bernal bilayer graphene, indeed, it has tons of these same types of stoner transitions. They're somewhat lower density and higher electric fields, but basically the physics is quite similar. The details are different. In the process of figuring out why Bernal bilayer graphene didn't superconduct, because of course it doesn't superconduct, we found that it does superconduct, but it superconducts under very strange circumstances. So what I'm showing you here is transport data. These are all different ferromagnetic phase transitions that you see sort of changing the color scale here because it's sharp changes in resistance, but there is indeed no superconductivity at zero magnetic field. And in the process of understanding why that was the case, we made this sort of surprising discovery that there's superconductivity only in applied magnetic fields. Okay? And in particular, only in rather strong applied in-plane magnetic fields. So you have no superconductivity at zero field, and then you apply an in-plane magnetic field, and you get superconductivity. Again, in sort of in between two phases, or maybe in a very narrow slice that corresponds to its own isospin polarized phase. Now, what we think is going on here is that there's some competing phase at zero field that doesn't superconduct. Now, what it is, I don't know. Okay, but there's some phase at low magnetic field that doesn't superconduct, but then you hit some transition, the system spin polarizes, and thereafter it superconducts, and actually superconducts to far above the Pauli limit. In fact, sorry, I actually don't have the data here, but the TC of this superconductor is 30 millikelvin, which makes the Pauli limit about 30 or 40 millitesla. It doesn't start superconducting until like twice the Pauli limit, and it continues superconducting to 30 times the Pauli limit. Actually, we have other data, the reason it stops superconducting here is actually because there's a very slight misalignment between the magnet and the plane of the sample. If you do this more carefully, you find it goes as high as we've had magnets go, so at least 30 times the Pauli limit. So, and it seems like the ground state is just spin polarized. So these are funny superconductors because they have pretty large coherence lengths. So 1 or 2 millitesla sometimes will kill them out of plane, but a Tesla in plane won't kill them. So there's like an anisotropy factor of at least 1,000. Okay, and what we think, there's some competing phase. We don't know what it is. I think it's interesting to think about. It sort of acts experimentally like a charge density wave in that you have a threshold nonlinearity in the transport, but it's not superconducting. It just looks like you turn up the current, and then there's some threshold current where the resistance drops a little, there's a sudden drop in resistance. So this is differential resistivity, and this bright blue means that there's a sudden drop in the a spike in differential resistivity just means the IV curve just slightly changes its slope. Okay? And this is also a phase that seems to show up at very similar temperature scales to the superconductor, and it's right in the same spot where the superconductor is. It's in between the same two phases. We don't know what this is, and it doesn't really make much sense to me because I would have thought, let's say you have competing singlet and triplet superconductors, whichever one dominates should win, and maybe you'd have a transition from a singlet superconductor to a triplet superconductor within plane field as you suppress it, but in fact, that's not what happens. You don't have superconductivity at zero field, and we don't know why. Okay, but I think an important thing for us has been, at the experimental level, that these are just very reproducible. These are two different samples, right? And if you look, both of them start superconducting just shy of 1 volt per nanometer, right? They start superconducting exactly the same way. They're essentially quantitatively identical. TC is the same. 30 millikelvin, 30 millikelvin, it's all extremely consistent. So this means that, it's now we can do experiments and actually have controls, which is actually useful. So one of the experiment I'll tell you about, and sort of if I have time, for the rest of the talk, is just focus on spin-orbit coupling. Okay? So there are two ways I'm going to tell about spin-orbit coupling. One is how can you add spin-orbit coupling on purpose? Okay? And the answer to that is yes. There's actually a very nice way to add spin-orbit coupling, right? Which is to support the graphene layer on top of WSE2. WSE2 is a semiconductor, and the band alignments are such that when you put graphene on WSE2, the WSE2, most of charge neutrality and a good range around charge neutrality in the graphene is just in the middle of the gap of the WSE2. But there is some, maybe virtual there's some tunneling process where graphene electrons can jump into WSE2, spend a little time there, come back, and pick up some small fraction of the spin-orbit coupling in the WSE2. Now, what's really useful about Bernal bilayer graphene specifically is that you can measure the strength of the icing spin-orbit coupling extremely accurately by some Landau level physics that I won't get into, but you can find in this reference. And it's not the same in every sample because that actually depends on the angle between the graphene and the WSE2, but you can measure it. You can know the number from sample to sample. Okay, so you can see what it looks like without spin-orbit coupling, and then you can add it and you can know how much you've added. So you know sort of what your single particle Hamiltonian is. Okay, and this is interesting because actually spin-orbit coupling and WSE2, the history here is that WSE2 is just, some people study it for spin-orbit coupling. They get wildly different answers for what happens to the graphene when you put it on WSE2. Some people use it because it's just, they like it better as a substrate, okay, and that might be because they think that it, pins things to make moire systems cleaner and so on. But one of the things that's been interesting is that it seems relatively ubiquitous that superconductivity seems to like being on WSE2. So for example, in twisted bilayer, you see superconductivity quite far from the magic angle in WSE2 supported devices. In twisted double bilayer, as far as I know, superconductivity has only been seen on WSE2 supported samples. But, again, these are a little hard. Like, what's the control experiment here? Nobody's ever made a 0.79 degree device with the same strain profile as this one without WSE2 and then been able to ask that question directly. It's really hard to do. Same thing here. I don't know. You have to sort of guess how many null experiments there were in people's labs with similar things. It's hard to do the control experiment. Here, it's kind of spectacular because, first done at Caltech from Stefan Nagy-Perge's group was actually the first to reproduce the superconductivity in Bernal bilayer in kind of spectacular fashion, because what they did, they put it on WSE2 because they like putting things on WSE2 for all these other reasons, and then they found that it's actually quite different. First of all, you do get superconductivity at zero magnetic field, and TC is 10 times higher, which is a very big effect. If you knew how to make TC 10 times higher, in any other material, you'd be very happy, right? So we were very happy when we saw this. And they saw that it's different. It's polyviolating, but maybe not nearly as strongly. So that's sort of what I'll talk about. So we, in collaboration with them, started to look at some of these samples kind of a little bit more closely, in particular focusing on the strongest spin orbit samples that you could find. And you find that indeed there's a bunch more, there's this large superconductor that they found, and there's indeed another superconductor, and it indeed seems to help okay. I'm not going to make it to the spontaneous spin orbit coupling, but I'll finish this part. So TC is much higher, and we're going to go ahead and play our trick of just like really trying to understand the normal state Fermi surfaces. And we see that for this first superconductor, which is quite low TC, it's emerging from a normal state that doesn't break any symmetries, except for the fact that the spin-orbit coupling itself is breaking the spinless time reversal symmetry that is normally there in graphene. Okay, so you have different Fermi surfaces than you did before, but they're sort of consistent with single particle picture once you put in this 1.5 MeV of spin-orbit coupling, which doesn't sound like a lot, but it's a lot. The Fermi energy is maybe only, a few times that. So it's a spin-orbit coupling that's almost as big as E Fermi, right? And certainly it's comparable or bigger than most of the interaction energy scales. Okay, so SC1 is sort of another one that sort of looks pretty standard. So this is what the sort of band structure looks like. You have this splitting in each valley between the different spins. Spin is still basically a good quantum number, but now your Kramer's pairs have opposite spin and opposite valley, and there's not the spinless time reversal. So now SC1 looks like it's emerging from the single particle picture, but then a funny thing happens as you keep lowering the density and approaching the Van Hoff singularity. The first symmetry that breaks here seems to be rotation symmetry. Okay, and so you can see that because there's this funny behavior of the quantum oscillations where one of the quantum oscillations corresponding to this big Fermi surface grows by exactly the area of one of the small Fermi surfaces. And actually when that happens, you see that the small Fermi surface doesn't change size, but you start to see a breakdown feature. It looks like those Fermi surfaces have depinned from the corners of this triangle and have come close to each other. And you can tell this is a quantum oscillation coming from magnetic breakdown because it scales with magnetic field differently. So it looks like there's a nematic transition, and that's interesting because actually the this nematic phase is exactly where the big robust superconductor is. It's just in the middle of this nematic phase. So you have this first order seeming nematic phase transition where you eat one of the big Fermi surface eats one of these small pockets, and then inside that phase you have a superconductor that has 10 times the TC of what you had before. And what's interesting, and I think maybe indicates why spin orbit is good, is that if you have a system now where you know exactly the strength of the spin orbit coupling, and you can look at the Pauli limit violation and how does it behave, and you see that in fact the TC is suppressed exactly. These are really zero parameter fits. We measure TC at zero magnetic field, we apply an in-plane field, and we know exactly the strength of spin orbit coupling, and we can just put that into a pair breaking formula and see that in fact superconductivity is suppressed exactly the same way as you expect for an Ising superconductor. And as far as I know, this is a nice system even among Ising superconductors because you know exactly what the spin orbit coupling is, right? You measure that in situ, you can vary it in different devices, and you see that, in fact, we think that most of these superconductors on WSE2 supported graphene are Ising superconductors. If you sort of look at the measurements that have been done, I think they're all consistent with this, but those other systems don't have a way of measuring that spin orbit coupling. Okay, so just to summarize, and I'll just cut out the last part of the talk. I'm happy to talk about, skyrmions and spontaneous spin orbit coupling offline. But, there are a lot of superconductors in crystalline graphene. This is most of them, right? In ABC, in Bernal bilayer, and Bernal bilayer on WSE2. There's a bunch of different ones, right? There are some that have no broken isospin symmetry in the normal state. Those are, can be Pauli limited typically in ABC. They're Ising, it looks like in the spin orbit version. There are those that come from spin polarized half metals, and those are, magnetic field independent. So they look indeed like spin triplet superconductors. They're just really just a spin polarized ground state. And there are those that come from states that seem to be nematic in their normal state. I don't particularly see a unifying element to all of these. I don't think there's like a magic, I'm finding it very hard to reconcile myself to the idea that there's like some magic order that, you just need this particular type of order and that's what gives you superconductivity or even makes it more robust so far. So that's just from an empirical point of view. I think it's a point that I want to make really strongly, which is that in these systems, you get superconductivity, and it's anywhere from 30 millikelvin TCs to 500 millikelvin TCs is sort of the largest that's been observed, and they sort of appear all over the place, and there's not much rhyme or reason to it as far as I can tell. So I'm not sure that, or rather, I tend to lean that, if there's a mechanism that underlies all this, it has to be something extremely generic, which kind of leaves two possibilities, I think. I are sort of skeptical of the idea that it's a particular isospin fluctuation that's really important for a particular order. I think it's more likely that it's either phonons, which I think is quite likely, or something like Cohn-Luttinger. One of the only things that's actually generic to pretty much every single superconductor here, besides the fact that it's in a system that does have phonons, is the fact that there's always a large Fermi surface and a small Fermi surface, and that the large and small Fermi surface is always sort of a similar range of ratios, few to 1, 5 to 1, something like that in terms of area. And, there's old proposals dating back to Doug Scalapino and Steve Kivelson that, thinking about Rashba semiconductors, that in fact that might make Cohn-Luttinger go from like a microkelvin effect to a, millikelvin effect. And so I don't know, I'm not sure exactly how to confirm it, except to keep finding them and seeing what we can infer generically. But I think that's kind of an important thing, maybe for some people in this room to think about. And so anyway, let me finish there and just take questions. Thanks.
Thank
you. Just a question from somebody who's not in the field. So is the only evidence for superconductivity that the resistance is getting sort of unmeasurably small?
You can also see signatures of phase coherence, like sort of if you go to the edges of superconducting domes or have samples that are dirtier, you can see these sort of Fraunhofer type patterns. What we haven't done yet is like make a Josephson junction.
No junctions.
We'll do that soon. But yeah.
But
it's low resistance. It's seeing some of these Fraunhofer type effects. It's the fact that it's suppressed by out of plane field extremely rapidly. It's a finite critical current. Those are the things. Mm-hmm. Yeah, these have very finite and very sharp critical currents. Mm-hmm. So that's another example. Okay.
Thanks. This was a stimulating talk. I have a question about the competition between singlet and triplet that you referred to earlier, so with reference to the absence of superconductivity in zero field, but you see it in finite field. Mm-hmm. Have you considered the possibility that there could be a competition between 3 triplet order parameters and the fact that the magnetic field breaks that degeneracy? One of the ways in which that might be supported would be then if you add some spin orbit coupling so that the d vectors could feel the anisotropy of the lattice, but you seem to have already done that. So that seems to suggest that. Another possibility would be to do the field in a different direction. So the question to you is, do you see this field-induced superconductivity when you turn on out-of-plane fields?
No, of course not, because there's just such a strong orbital effect at that point. So you certainly can't, and you don't. But that's not too surprising. Mm-hmm. I'm not sure I catch the flavor of your first comment, because, I mean, I think it would be interesting to understand if you have competing superconducting, pairing channels. My understanding was always, it's super naive, and I'm by no means an expert in superconductivity, but I thought, if you have a few competing ones, whichever one wins, that's the superconductor that you get. If there's going to be a competition, you need a competition where, the fact that it's a tie means you don't get superconductivity at all. And if that's a scenario that is plausible, then maybe that's what's going on. That seems to be what the experiment says. Or there's something else that's competing that beats the superconductors. But I don't have a mechanism for any of that. It's just clearly the experiment.
So is the experimental data only with in-plane fields, or do you also tilt the field out of the plane as a function of angle?
You can put the in-plane field, then you make the superconductor, and then if you put even a little bit of out-of-plane field, you kill the superconductor right away. Yeah.
Thanks.
Yeah, we got 2 questions over there, 3 questions now. Just to start from back.
Andrea, great talk. It's been really fun to follow this. Can you go to the slide where you show the pneumatic transition? I just want to ask a completely clarifying question.
Yeah.
I guess my first clarifying question is this the only pneumatic transition you observe, or are there other pneumatic transitions like this?
So there's a paper that I should have had a slide from here, but I just forgot to add it before the talk. Leo Lee at Brown has done some more direct measurements of nematicity. They see nematicity all over the place. And it wouldn't surprise me if there's lots of these phases are nematic.
I see.
We have typically we just didn't think to do that experiment. So, but what we can do is count, and we're good at that, and we can count up quantum oscillations. This happens to be really clear because the sum rule, the only simple sum rule that gives you Luttinger, theorem is 1 + 2 per flavor, and there's just no way to do that without nematicity.
Yeah,
so here it hits us on the head and we can't get out of it. Actually, I think if you just measure it directly, it turns out it's all over the place. So yes, there's lots more nematicity around.
Gotcha, thanks. I wanted to ask about that because there was
So I think a super interesting question experimentally is, is SC1 associated with a nematic that you just don't see in quantum oscillations for some reason? Because you can break rotational symmetry without changing sizes necessarily, or without changing sizes of Fermi pockets. That that could happen. We just measure there, the topology of the Fermi surface in some ways, but we can't measure its geometry. So it could be that that's nematic, and nematicity in principle could be everywhere, and maybe that's indeed like a unifying feature.
So do you mean nematicity in the regime where you only have big pockets? You wouldn't see this in quantum oscillations?
We wouldn't see it in quantum oscillations unless it gives us different numbers. I mean, it doesn't seem to deviate very strongly from the single particle picture, but they could change shape in a way that, conserves the area to within experimental error, and we wouldn't know.
Great, thank you so much.
Sure.
Were you doing all these tests that this is really superconductivity systematically on all the different phases you showed? So you flashed very briefly, for instance, a plot where resistivity was in fact only dropping a little bit and was not going at all to zero, and you said, this superconductivity, and then I said, my God.
I think we've sort of understand a fair amount about this, so I'm pretty confident that when we say something is a superconductor, the things that...
But can you show that plot? Sure, I mean, you just said it's superconductivity, and it was just dropping by half or something?
Yeah. So I mean, the issue, which was an issue also in ABC. This is the one, Yeah, so of course this is not great, right? But... very small out-of-plane magnetic field, strong nonlinearity, this is current. Strong nonlinearity almost immediately quenched by an out-of-plane magnetic field. That's kind of usually been a pretty reliable signature in these systems. So when you see something that's got a strong and sharp critical current, and then it's killed by an out-of-plane magnetic field immediately, so far the track record has been, resistance is not zero, but these are right at the limit of our electron, of our...
So you were not cooling or something, you think?
We can't cool. It's also an issue that, you apply finite current. This particular sample had very long leads. This is just what they all look like, and then if you improve it a little bit, then they look nice. Like this one, it's pretty unambiguous. It gets sharper. It's very zero. And again, like at this point, a little bit of it is just lizard brain pattern recognition, but you have this happening right before a Stoner transition, like it hits you over the head so many times that you sort of, that's basically what we're going on. So it's strong nonlinearity quenched by out-of-plane magnetic field. The fact that this happens right next to then another Stoner transition, I mean, I'll give you even odds if you want to bet.
Thank you.
It'll turn out to reproduce,
Is there anything you can do to deduce the pairing symmetry?
Yeah, so I think actually something that we've thought about, it's a complicated experiment, but I think it's something that we do is you can make quantum point contacts, and you can do them as a function of angle relative to the lattice, for example, and you can try to tunnel in, and I think that's all possible. STM is going to be challenging on these systems because of the large electric fields, but some of them might be accessible.
So for the spin polarized one, could it be P plus IP?
I mean,
is there any?
Can be.
What?
What I think is that it's Valley singlet, and that it's all Valley singlet.
Okay.
Because until you have good evidence to the contrary, that seems like an obvious thing to have happen.
Fair enough. Yeah.
With spinless time reversal.
Thank you.
So in the table that you had at the end, summarizing everything, you showed that AB with tungsten diselenide tanks up TC by a factor of 10. Have you tried doing that with ABC?
Yeah, we've tried.
And?
Nothing to talk about yet. I mean, we've just succeeded in making a sample that has such a geometry. Sadly, it doesn't have very many contacts on it, so we can't measure transport, but we can measure magnetometry and capacitance, and it's different. And I'm dying to know what transport will show. There's actually, credit to, I think it was Paco Guinea's group. They actually made a prediction before an experiment was done, which it's not going to help as much as in Bernal. And I'm curious to see if that turns out to be true.
And, there are other terms in the series, so you could go to ABCA, ABCAB.
Roughly speaking, it's squaring 1% for every, you're at, that turns out to not be so easy. I would love to do it, but we have not figured out a good way to do it. Andrea Young's group, they claim that they have some tricks, and they have a paper on like multi-layer rhombohedral graphite, which I thought was, I think it's possible. We haven't been able to figure out how to do it. Maybe somebody more clever than us will figure out how to do it, or maybe we'll eventually figure it out. But I think it would be very interesting, because I think ABCA might be the sweet spot, as far as I know, from like band structure calculations. That's where maybe the density of states gets higher before these other terms start to get annoying.
How much can you control the screening in these devices? And might that be able to distinguish between like some electron-electron interactions or?
So we have done that experiment very roughly, where we've tried to screen things on, let's say, a 3 nanometer, or I guess the image charges would be like 5 or 6 nanometers away. It didn't make a difference to the ferromagnetism. The sample, for various reasons, didn't have good enough context to look at superconductivity. So the ferromagnetism seems to be pretty much, contact interaction type of thing, which I think makes sense. We haven't been able to look at that for superconductivity. We don't have any data on that. Yeah.
Is there ever anything interesting in the temperature dependence of the resistivity at any of the places?
Yeah.
Yes?
Yeah.
Where? What? Why?
I mean, we're still thinking about it. I mean, at high temperatures, at quite high temperatures so far, what we've looked at, it looks very consistent with I think Shankar has a paper on electron-phonon coupling. It looks like that. But there's an intermediate temperature regime where it actually has non-monotonicities. And we're not sure where those come from. And that's something that we're thinking about. But it doesn't have, for example, strong linear T. It has like linear T that's exactly more or less what you'd think from phonons, to within a factor of 50% or something like that.
Hi, so monolayer graphene also has settle points, so what's the story there?
The story is that those are like 10 to the 15 electrons per square centimeter, and if you know how to do that, you should definitely do it. It'll be a room temperature superconductor.
Meaning you can't tune the density?
You can't tune the density.
So in the Bernal study, since you do have quadratic dispersion at low energies in these materials, can you estimate what would be the low energy optical spectral weight? It's reasonably quadratic, so it's of the order of Fermi energy.
I suppose it's we're mostly in a regime where it's not that reasonably quadratic.
Okay, thank you.
I don't know. That allows me to not answer the question that I don't know how to answer. Yeah.
Thank you.
Okay. Do you have any other question? Everybody's dying for coffee. Okay.
Great. Thanks
so much.